Melissa, you're going to have a brief introduction, or I can just directly start?
I would say just directly start.
Okay, good. All right. So, all right. Good morning, good evening, and good afternoon, everyone. And this is the first day for the introduction of the multi-GNSS precise quantum positioning and the training course for our software prior to PPPAR. So it's good to see you here. Although we are on the in the virtual environment, and I hope you are doing well in the pandemic situation. And today, I'm going to have a brief introduction of the basics of GNSS techniques and its relevant knowledge on the GNSS constellation development of the past decades. And then we have two of my students who are going to have some more in-depth introduction on the software itself and how we can install it. So, anybody? All right. Okay. So here, this is the schedule that we're going to have in this week. So we have two courses. The goal of this course is to demonstrate the ambiguity resolved PPP solutions and teach how to use the parameter PPAR software. So I have listed the two references here. The first one is to demonstrate the benefits of single station solutions. So we used to have a network analysis using GPS. We have multiple stations there, and we have to form baselines to achieve the high precision solutions. And then in this paper, we talk about why we would better use the undifferenced solutions to have a comparable position and precision to the traditional reference solution, relative solutions. And the second one is a reference for the software itself. So we use in this paper, we introduce the basics of how to install and how to use heavier first processing using our software at a single station and with ambiguity fixed solutions. For the first day, we will have three talks. The first one is done by myself and on the basics of multi-GNSS and the precise point positioning, which is in short as PPP, using the multi-GNSS data. And then the second one will be the introduction of the prior PPAR software, and we will have some demonstration on the installation of the software and some prerequisites to using this software. And the third one is to start your first GNSS processing for using some basic data and without a lot of difficulties in managing the data or the preparation for the data. And the second day, this will happen on Friday of this week. So we're going to have some more in-depth analysis of your GNSS data using the software at a single station, and we use the ambiguity fixing technique based on the phase-wise products. And then we can see how we can improve the solution and how we can achieve the similar position precision and other statistics to the traditional processing technique based on double difference solutions. And the final one will be some advanced processing features about this software, such as the very high rate data processing for some kind of seismology analysis. And then we can have some multi-day processing for the time transfer using the hydrogen receiver clock. So these are the three speakers and we have today, and Dr. Lin Jihang and Dr. Zheng Jing are two of my PhD students. So they are going to have some more introduction on the software itself, and they are more familiar with this software than me. All right, so let's have the first. I hear some checklist. Okay. All right, sorry. So I'm not going to have a lot of details on the application of GNSS jealousy, but because I just assume that everybody here is familiar with the high precision GNSS basics. So for Earth observing from the space, the GNSS technique is the unique one because it has a global constellation to observe the Earth crust from on a global scale, and without any interruption, you can observe some high precision positioning, high precision displacements, or some troposphere variation using the satellites, which are distant, very distant from you, which are located about 20,000 kilometers away from you. And you can have this using this GNSS data to continuously observe the Earth's crust. And then you can have a knowledge on the earthquakes, volcanoes, eruptions, and flooding, as well as the post-glacial rebounding. So this knowledge is very important to our understanding of the Earth's evolution over the past decades, and we can have some more precise prediction of the future evolution of the Earth's crust. And this will help us to understand how we can establish a good relationship with the Earth. All right, so this is the current status of the GNSS. The GNSS is short for Global Navigation Satellite System, and now we have 4 constellations, which are GPS, GLONASS, Galileo, and Beidou system. And we have 2 regional systems, such as the QZSS, developed by Japan, and the NAVIC, developed by India. So we're not going to talk about anything about the regional system, but here we focus on only the 4 global constellations. So here we can see at the moment we have more than 100 satellites to be deployed in the space for us to monitor the global change of the Earth's crust and even the atmosphere changes. So here we can use multiple multiple frequency signals from the satellites to do all kinds of combination and to some more to facilitate our data processing, to improve our precision and as well as the processing efficiency. So we come to the first one, the GPS constellation, which is the most successful global constellation to monitor the Earth's crust, and it has many application cases for industrial in the industrial fields, as well as to improve the economic development in the world. So that's one of the reasons why the many countries are developing their own navigation satellite system. So the GPS, so the latest development of GPS constellation is we have about 10 satellites to be being launched to the space as GPS Block 3 satellites, which is designed to have 3 times more accurate accurate observations to improve the people's positioning experiences, and it has 8 times more improved anti-jam capability. And then the next generation GPS satellites will be GPS Block 3F, and it's going to, so they are going to have 22 additional GPS 3F satellites in addition to the 10 previous one, and this can form a 32 satellite constellation to have a beautiful global coverage to monitor the crust motions. Then the GPS has three satellites have 3 frequencies. The first one is L2, and the second one L2, and third one is L5 signals. So here we have some new signals to be embedded in the GPS frequencies, such as L2C and L1C. So this they use some advanced coding technology to have some more pseudo-range measurements to be retrieved from the carrier phase data. So here we can use the L2C to recover the L2 signals to have more robustness for the carrier phase tracking, and L5 signals is developed to improve the positioning efficiency. For example, to have some more efficient ambiguity resolution, And we can use L5 to, in addition to L1 signals, to have more robust positioning, because the L2 signals are susceptible to some interferences, and because of their power is relatively lower compared to L1 and L5. And here, and then we come to the GLONASS. So the GLONASS signals is quite interesting because it's based on the frequency division multiple access technique. That means for one station on the ground, whenever you receive the signals from the GLONASS satellites, for each satellite will have a different frequency, and that will make some difficulties for you to process the high precision data, and you will have a big problems for the ambiguities in the carrier phase data. So we're going to have some brief concept introduction of the ambiguities later on. And now the GLONASS K and the 2 K generation satellites are being launched to the space. And this in this generation, the GLONASS satellites will broadcast the CDMA, I mean the code division multiple access data signals instead of the FDMA signals, and that will have some more compatibility with the GPS and some other constellations in the future. And then we come to the Galileo constellations. So this is the very advanced system. It was built to support commercial applications of GNSS, and it is operated by the European Space Agency. And now we have about 21 satellites in space. It is still under deployment, and the goal is to have 30 satellites in the space to provide continuous positioning services and secure the positioning services for the civilian applications. And now we have there are two satellites, the E14 and the E18. These two kind of satellites, because of the failure of the satellite launch, these two satellites are not in the circular orbit, but in the ellipse orbit instead. So these two satellites are used for demonstration of some scientific applications, but they can still be used for positioning, although they are not in a good health and can sometimes damage your solutions. The current status of the Galileo multiple frequencies, and we have E1, E5, and the E6 signals. For the E5 signals, it can be divided into E5A and E5B, and these two kind of signals can be used separately or being tracked in a combination. So then, in this case, it can be more resistant to multipath effects and can be more easily tracked in a very difficult situation, like under the trees or in some urban canyons. So this will improve the Galileo performance, especially in some kind of GPS, some kind of GNSS adverse environment, which is very interesting, very important to the applications for such as the self-driving vehicles. There's one thing that needed to be noted is the Galileo clocks, stellar clocks. The stellar clock is the basis for GNSS to broadcast stable carrier phase data for high precision positioning. And here, the Galileo satellites are equipped with the high hydrogen atomic clocks instead of the usual the rubidium or celsium clocks. And this kind of clocks have two orders of magnitude more stable than the traditional atomic clocks. So then we can have the stellar clock product to be interpolated at a lower interval, and then we can still maintain the positioning precision without losing any kind of positioning advantages. So this is the clock stability description for the Galileo onboard atomic clocks. And this is the status of the Beidou system, which is developed by the Chinese government. And we currently have BDS2 and BDS3. The BDS1 system was established in the year of 2000 using 3 geo satellites. it can provide services within China, but you have to send the signals to the satellite first before you can get your position. So it has a low precision. So it's just a demonstration system. The BDS2 was established before the end of 2012 to provide services over the Asia Pacific region. And this is similar to GPS, and can it broadcast electromagnetic waves, and the users can use the signals from 5 GEO and 5 IGSO and 4 MEO satellites to do high precision positioning in Asia Pacific areas. And then in the year of 2020, the Chinese government announced the full constellation of BDS3, which is a global constellation instead of regional one from BDS2. So it is composed of 24 MEO satellites, which is a middle Earth orbiters, and in addition to 3 GEO satellites and 3 IGSO satellites. The IGSO stands for Inclined Geosynchronous Satellite Space Orbiter. So here you can see this is this satellite constellation is composed of 2 levels of satellites. So then you can see some improvement in the when we can do some global reference frame maintenance, and see some different stories here. All right, so now we have 15 BDS2 satellites and the 29 BDS3 satellites in combined, and this can provide some more signal redundancy for us to maintain the robustness of positioning on a global scale. This is the current BeiDou multi-frequency status, and we have B1 signal, B2, B2A, B2B, and the B3I signals. So this is similar to the Galileo frequency spectrum, and we have B2 signals, which can be divided into B2A and B2B. And this kind of 2 signals can have a higher capability to resist multipath effects. So they can also benefit the positioning in difficult areas. And then here we want to emphasize the B1C signal, which is compatible with the GPS L1. They have the same frequency, and this can enable interoperability between the 2 systems. So then the users can use the signals from the 2 constellations without any problems of upgrading their receivers. And this story also happens to Galileo E1 signals, because the E1 signals has the same frequency as the GPS L1. So then we can use the signals from 3 constellations without any problem. And then can, because the more satellites we have, the more robustness you can have in your positioning. Okay, so I'm not going to have a lot of knowledge there to bombard you with the basics of the GNSS constellations, because you can find some kind of knowledge from the internet. So here we come to some basics of the GNSS observations. So we are going to process these GNSS observations to get what we want, such as the displacements and the troposphere troposphere status. So that's how we can reduce the GNSS observations from pseudorange, such as pseudorange and the Carrier phase, to those we are interested in. There are 2 basic observations from GNSS. The first one is the pseudorange. So from this name, you can see this is not actually not the true distance between the satellite and the receiver. This kind of observations are contaminated by the receiver clock errors, and as well as atmosphere errors. So here, before you can process this data, you have to correct for all kinds of, such as satellite clock offsets and relativistic clock correction, some kind of instrument delays, and the atmosphere delays, as well as the receiver clocks. So after all of this, we can have a relatively higher precision than using the raw pseudorange. So the pseudo range data are noisy, but unambiguous because they describe the distance, general approximate distance between the satellites and the receivers. And then the second one, and then this is how the pseudo range data are calculated by the receivers. So they use the receiver will produce the replica signals to be compared with the signals received from the satellites. So after they find a high correlation between the two signals, they can calculate the time of arrival of the signal, and then this time of arrival will be multiplied with the speed of light to get the pseudo range. The second observation, a basic observation of GNSS is carrier phase. So this is the observation that we are going to use for high precision positioning to achieve the millimeter level and the centimeter level positioning accuracy in our data processing. So the carrier phase is it's not a range measurement. It is actually the receiver will actually measure the fractional part of a full cycle of carrier wave rather than the distance between the satellites and the receiver. So this is unlike the pseudo range measurements. So here we can only measure the fractional part of a full carrier wave. So then we have an ambiguity terms there, which we're going to talk about later on. This carrier phase measurements are very high, precise compared to the pseudo range measurements. It can achieve a millimeter level precision, although this kind of measures can still be contaminated by all kinds of errors such as clocks and atmosphere delays. So we needed to do some more modeling of the observations and the mitigation of the errors before we can do the high precision processing. So then we come to the carrier phase ambiguity. So this ambiguity term is very strange to the outsiders who are not familiar with GNSS technique. So the ambiguity describes the integer number of full cycles in the signal propagation path between the satellites and the receiver. So you see here, this N0 is the ambiguity term. Because the GPS receiver can only measure the fractional part of the full cycle, so the full number of integer cycle within this path is actually unknown. This is N0. So this term has to be estimated along with other parameters like your positions and troposphere delays and the clocks. So we have to tolerate this kind of ambiguity terms, and before we can do high precision positioning. And here we need to introduce the term like the phase bias. The phase bias means we have some kind of things that we don't like in data processing, because the least squares adjustment cannot distinguish between integer parameters and non-integer parameters. So the N0 is an integer parameter, but we have some other areas to be assimilated into the ambiguity. And finally, from the least squares adjustment, we can only have real valued ambiguity estimation. So then we called this kind of real valued ambiguity term. They contain the phase bias terms, and these phase bias terms are not known, and we have to separate them before we can recover the integer property of the ambiguity terms from in the carrier phase measurements. So we call this identifying integer ambiguity as the ambiguity resolution. So this is the basic concept because we are going to use a lot of ambiguity resolution terms in our later slides. All right, so here the main focus of this slide is to how to eliminate the phase bias to achieve ambiguity resolution to recover the integer property. So we needed to separate this BR and the BS terms from the N0 terms to recover the integer property of the N0. So before we talk about that, we would like to make a comparison with the standard point positioning, and this is actually the standard service provided by GNSS. So we use only the pseudo range data, and because of their high noise, and we cannot, or it is not necessary to provide to use a lot of high precision models to correct for this range measurements. So finally, we can only achieve a middle level positioning precision using the standard point positioning. Pseudo-range measurements, so geometric distance, and these are the clock terms. So, so I'm not going to have some more introduction on this equation because everyone doesn't like the equations here. All right, so then we come to the precise positioning using GNSS. So the first one, the traditional one is RTK, which is based on a baseline. So use relative positioning technique. But here, the most important thing for us to note is that we needed to use the carrier phase measurements instead of the pseudo-range measurements to do RTK, to have the centimeter level or even the millimeter level precision. But here, for the RTK positioning, you have to use the basis station here, and these basis stations have their coordinates known, and you can back calculate the correction data like the atmosphere delays and the orbit and clock corrections. And this correction data will be disseminated to the rover station here. And this rover station can use this correction data to improve its positioning precision. So this is the basis for RTK positioning. This is the RTK network over the continent of the North America. You can see they have a lot of a dense network in the eastern part of the US. And because of these reference stations, so because of the short baselines, and you can actually achieve a very fast positioning, centimeter level positioning performance within a few seconds, and but over a very short baseline, for example, less than 10 kilometers. So that means that we have to establish a lot of reference network like this to maintain that kind of high precision and high efficiency positioning, RTK positioning. So that will cause a lot of heavy station maintenance and frequent communication between your reference station and your rover stations, and that will definitely increase your cost to maintain this kind of service. So then we come to the main topic today, that is precise point positioning, which is the shorter name is PPP, which is quite elegant, right? And here, over the past decade, a lot of people have focused their studies on developing a technique that can have the advantages such as high precision and highly efficient positioning of the RTK, but can escape the limitation of a close reference of nearby reference stations. So then we come to the precise point positioning because it is based on a global reference network. So the users needn't know where their reference stations are, and they can still achieve a comparable position and precision to those of RTK. And then this is quite advantageous because we do not need any nearby basis stations anymore, and we can still achieve a high precision network analysis on a global scale. But then we have to pay attention to some kind of you can have the PPP to facilitate your work in the GNSS network analysis, but we have to pay attention to some limitations of the PPP. The first one is the error correction, and because we don't have any base stations to provide the correction data, so we have to use some other technique to mitigate the errors within the GNSS measurements. We have to use some kind of linear combination between different frequencies of data to eliminate some errors, such as the ionosphere, and we have to use some precise models, such as those from IERS 2010, very precise models to mitigate the residual errors, like the solid Earth tide and the long tide ocean loading. So these errors will be quite complicated in our PPP processing, and you have to make sure that every model is correct before you can maintain the millimeter level positioning. The second one is the ambiguity resolution. Why do we have difficulty in ambiguity resolution in terms of ambiguity resolution in PPP? So in the relative positioning, because we have two stations and we have multiple satellites, so using the differencing technique, using the correlation between the areas from the base station and rover station, and we can use the differencing technique to remove the errors such as the orbit errors, clock errors, and atmosphere errors. But if you have only a single station, or you have one station, you don't have this differencing capability, and you have to then you have to tolerate some kind of errors to be absorbed into the ambiguities. So the ambiguities from PPP can hardly be resolved or can hardly to be fixed to an integer because of the phase biases. So we have to find some way to overcome this difficulty. All right, so then so we mentioned a lot about the errors within the PPP processing. So then the first one is the errors related to the satellite. So we have so this is a table listing all of the errors related to satellite orbits, clocks, and attitude and phase center offset, and the relativistic errors and the code bias and the phase bias from the satellites. So we can pay attention to the uncertainty or the errors of these items. So we can nowadays we can determine the orbits as precisely as 1 centimeter or 10 millimeters. So this is very high precision. It can be provided by some third parties like the International GNSS Service, which is going to be talked about later on. And we have the clock offset stellar clock. Although it is based on the atomic clocks, but we need to still make some further corrections on these clock errors if we want to achieve a millimeter level of precision. And then we have the antenna offset, phase center offset, and this can be up to 10 centimeter errors, and because the phase centers can be changed in the space, because of the space environment and because of the consumption of the power, the fuel within the satellites. So that will change the center of the mass of the satellite, and that will in turn change the phase center offset of the satellite antennas. Okay, then the first one, I'll come to the first one, satellite orbit. Now the satellite orbit from the final IGS orbit product is better than 1 centimeter actually for GPS constellation. And for the Galileo and the GLONASS satellite orbits, we can have similar precision to that of the GPS. The broadcast ephemeris have the orbit error of up to 1 meter, but we can use the broadcast ephemeris for real-time positioning. So, but if you are going to use to do some post-processing, you can choose the final satellite orbit product to achieve millimeter level positioning precision. And this shows the errors from the IGS rapid and final orbit, shows the comparison. Okay, this is a satellite clock offset, and we have a lot of texts here, but we in the broadcast ephemeris we use a second polynomial equation to describe the precision or describe the behavior of the clocks. In the precise point positioning, we usually need to use a tabulated clock product to provide the clock corrections. So usually the satellite clock product has a has a sampling rate of 5 minutes, 30 seconds, or even 15 minutes. So then we have to interpolate this clock offsets to provide, for example, for high rate positioning. And then this interpolation can cause some noises in your processing. For example, 5 minutes clock, and you can for the interpolation for high rate data processing, and you can see the error for the the carrier phase residuals are increased to a large extent. This is a satellite APC, a satellite antenna phase center, which is actually the distance between the transmitting position of the satellite signal and the satellite center of mass. So this two position, this distance will matter in your high precision positioning, which is related to your global reference frame. For example, the scale of the reference frame will be impacted by this satellite APC errors. So normally, this antenna phase center errors will be associated with your satellite attitude. So you have to use the attitude product from the IGS to precisely correct for the antenna phase center errors. So as you can see here, this is a comparison between these two kind of strategies. So when you are not going to use the correct attitude product to do PPP, you will have a 1 to 2 centimeter positioning positioning errors in the kinematic positioning mode. Okay, then we come to the errors related to the propagation path of the signals. So because so you can see, you can easily think about the troposphere delays and ionosphere delays. The troposphere delays can be divided into two parts: the dry part and the wet part. The dry part can be corrected using some models, but the wet part has to be estimated along with some other parameters. And the ionosphere delay have the first order of ionosphere delays can be mitigated using linear combination of signals, and the higher order ionosphere delays can be calibrated using some pre-existing graded ionosphere product. All right, this is the description of the zenith, the troposphere delays. So we can see here, the troposphere delays are divided into two parts. The zenith dry delay can be precisely calculated from standard meteorological elements. And this kind of meteorological records can be obtained from the local sensors around the GPS stations. And you can always use some standard elements to meteorological recordings to do this estimation of the ZDD. The wet part is quite is difficult. Is another story because we cannot use only the standard meteorological recordings to precisely correct for this weather delays. And then you have to make an estimation of this weather delay along with some other parameters to precisely have a precise estimation of your vertical component. Okay, we have to speed up. We don't have enough time to finish all of this. And then we have the mapping function of the troposphere delay. Why do we need to have a troposphere, have a mapping function for the troposphere delay? This is because for each slant path of the satellite signals, and we cannot estimate the slant troposphere delays within the least squares adjustment. And this because that will cause the linear correlation among the parameters, and that will cause the rapid effect. So then we use the mapping function to describe the vertical troposphere delay, and then we use these mapping functions to project the zenith delays to the slanted directions. Nowadays, we have the Vienna mapping function 1, which is more precise than the traditional neo mapping function and the global mapping function. And they can this is always used by the international reference frame maintenance, and they can provide more precise vertical components of the positions of the tracking stations. And then we come to the ionospheric delay. So as we have talked about, the ionospheric delays is associated with the dispersive medium in the atmosphere. So they are dependent on the signal frequencies. And then the first order delays can be mitigated using using a linear combination. We call it the ionosphere-free combination to eliminate the first order delays. And this the first order delays account for about 99% of the ionosphere delays in some normal conditions. So here we can see that the first order delays can be up to 100 meters, but the higher order delays, the second order delays of the ionosphere is only about one centimeter or so for the L1 and L2. So the major problem here is to mitigate the first order delays from the ionosphere. We used to use the Kalabuchi model to do the correction, but this can only be used for standard point positioning because this kind of correction capacity is only 50% or even worse. So then we cannot achieve a high precision positioning using the Kalabuchi model. And then the usual way for PPP is to do the dual frequency undersphere free combination. So here we use the P1, P2 signals and L1 and L2 signals to do this kind of combination to have the PIF and the LIF. And these two observations are normally used by PPP processing. And then we come to the multipath effect. And this is an interesting and annoying effect for us to do high precision positioning. It is caused by the interference of the reflected signal near the receiver to the direct signal from the satellite. So the non-offset and the 9-offset and the 9-offset signals. And these two kind of signals are both detected by the receiver, and the receiver cannot distinguish between these two kind of signals, and that will raise the noise of your pseudo-range and the carrier phase observations. The pseudo-range data are more affected by the multipath effects, which can be up to 10 meters, but the carrier phase are less affected. So the normally the largest noise caused by multipath on the carrier phase is just only a few centimeters, but this can still make a limitation on the carrier phase data processing and will reduce your position precision to the centimeter level. But unfortunately, we don't have any good modeling method to mitigate multipath, and we have to establish our stations, our static stations, in some good environment to avoid the multipath effects as much as possible. All right, this we come to the phase wind-up. Phase wind-up effects is caused by the relative motion of the satellites and the receivers. So because of the relative positions or relative motion is always changing in the space. So then you have to make this correction, wind-up corrections to improve your carrier phase data processing. The satellite-based wind-up correction can be corrected using along with the satellite altitude products. And the receiver-related wind-up effects can be absorbed by the receiver clock offset, because this kind of correction cannot be distinguished from the clock errors of the receivers. All right, finally, we come to the errors related to receivers. So we have the solid earth tide and ocean tide loading and cold tide. These are the three major tidal errors for the GPS for the GNSS stations. And there nowadays we can have the precise models from the IERS, conventions 2010 to correct them as precisely as 1 millimeters. So in our processing, we normally don't need to worry too much about this loading models. And some other effects that the clock offset originated in the receivers, and this can be estimated along with your positions, so without any problems. And then we have the receiver phase center offsets and the phase center variations as well. So this is a similar story to that of the satellite phase center offset and phase center variations. And because the receiver antennas are on the ground, so we can use some machines to measure the phase center offset and the variations. And these values are usually provided by antenna manufacturer and also as well as by the International GNSS Service. So this is the receiver APC. They have the similar characteristics to that of the satellite antennas. Normally we use the ARP, the antenna reference point, to describe the phase center offset and the phase center variations. And this figure shows the carrier phase residuals if we don't make any correction for the receiver antenna phase centers. You can see here we have some kind of very regular motion, regular phase residuals, and this will cause some fake signals in our data processing, and we'll have the displacements to be contaminated by this kind of spurious signals. Okay, then we come to the solid earth type and the pole type, and these two can be corrected using based on the theory from the IERS Convention 2010. And one thing that needs to be noted is the radial component of the solid earth type can be up to 0.4 millimeters. This is very huge, right? 40 centimeters, but we can make corrections on them to be precise, to be as precise as 1 millimeter. So there's no worry about that. And then the ocean tidal loading, and this ocean tidal loading is a component that is related to the water mass redistribution of the oceans. So you can see here this kind of the largest component of this loading effect is in the vertical component, which can be up to a few centimeters as well. And we have to use an online tool to calculate the loading coefficients, including the amplitude coefficients and phase coefficients to precisely model this kind of errors. So here the left figure shows the positioning errors without the ocean loading corrections, and then we can see some large fluctuation of the positioning time series. But after we make this correction, we can see the position precision can be improved a lot. So this is in a kinematic positioning, kinematic PPP processing. All right, so after we finish all of the introductions of the errors within the GNSS observations, we come to some kind of very, very complicated equations here. But actually, you can see some similarities between each line of equations. You see here, we have the distance distance measurements, geometric measurements between the satellites and the receivers, and we have the clock errors here, and this is troposphere, and this is ionosphere, and we have the phase bias and the code bias here, and we have the phase bias here. So the code bias and phase bias products are very critical to the identification of integer ambiguities. So these four equations are going to be combined to be transformed into two equations like this. So to form two ionosphere-free combination observations based on pseudo-range and Kerr phase measurements. I'm now going to make some more explanations of these two equations, and we come to directly to the ambiguity resolution at the single station. So why do we make some specific explanations on the ambiguity resolution at the single station rather than any other knowledge of the observation equations? This is because the undifferenced or ambiguity resolution at the single station is the main features of this software. So we can see here, after we make this combination, we actually have this term to be the ambiguities, and this ambiguities will lose its integer property, not only because of the phase bias terms here, but also because the combination coefficients for this ionosphere-free observable is non-integer quantities. So then we have to do some more decomposition. The first one is to use the single differencing between the satellites to remove the receiver-related phase biases, because this phase biases actually is related to both the satellite phase bias and the receiver phase bias. So after we make this single differencing operation, we come to our further decomposition of the ionosphere-free ambiguities. So this ambiguity does not have the integer property, but it can be decomposed into a linear combination of the wide lane and the narrow lane ambiguities. So the wide lane and the narrow lane. So you only need to remember that this combination has a longer wavelength of approximately 86 centimeters, and the narrow lane combination has an ambiguity of a wavelength of approximately 11 centimeters, which is only half of the wavelength of the raw L1 and L2 GPS ambiguities. So in this two-step, we can reestablish the integer properties of the undifferenced ambiguities, like the widening and the narrowing ambiguities. All right. So after that, we come to the limiting factors for the ambiguity resolution of the widening ambiguities. So here we normally use the Melbourne-Wheeler combination. And so this is a very interesting combination because it is based on the pseudorange and carrier phase simultaneously. And because of the pseudorange data, and this combination has a lot noise, and we have to use a long period of data, such as 10 minutes or even 20 minutes, before we can reliably identify the integer cycles within this combination. That means the widening ambiguities. And we have to also think about the antenna phase center corrections on this combination and the widening phase biases, which is provided by the International GNSS Service. And we should think about the insufficiently corrected errors, such as the smoothing, insufficient smoothing of the pseudorange by the carrier phase, and pseudorange observation quality sometimes quite bad when we wanted to identify the long wavelength ambiguities within these observations. Okay, this is for the narrowing ambiguity resolution. So after we fix the widening, and then we can introduce the widening ambiguities into our ionosphere-free ambiguities, and then we can recover the narrow ambiguity with the integer properties. So then in the next step, we can use the lambda method or integer rounding operation to identify the integer quantities of the narrowing ambiguities. Actually, I hope everyone is not confused by all of these equations, but you don't need to understand all of them. You need to just remember we have two steps to fix the PPP ambiguities. The first step is to do the widening ambiguity resolution, and the second one is to do the narrowing ambiguity resolution. So only when both the steps are successful before we can resolve the PPP ambiguities and to achieve an ambiguity fixed solution. All right, now in the final part, I'm going to introduce the International GNSS Service and its PPPAR, or the phase bias service. The IGS is one of the most successful organizations affiliated to the International Association of Geodesy. So it was founded in 1992 because at that time we have almost the full constellation of GPS, and the people at that time found that the GPS constellation can provide very precise positioning results on the global scale, and this can be used to monitor the global cross deformation. And at the moment, IGS is composed of about more than 200 research institutions from the global So from more than 100 countries and regions. So the mission of the IGS is to provide the highest quality of GNSS data, products, and the services on an open basis to support, for example, the establishment of the Earth reference frame for the Earth observing GGOS, the global Earth observing system, and to do for the civilian positioning, navigation, and the timing services. For example, to be used in self-driving vehicles and RTK positioning for the control surveying, and other technology applications for the benefit of science and the society, like the geohazard monitoring. And this is one of the major concerns of the IGS. And now the IGS has a global reference network of about 500 permanent stations. So these stations, nearly all of these stations are capable of observing multiple data from multiple constellations. We call it the multi-GNSS stations. they can receive signals from not only GPS, but also GLONASS, Galileo, and the Beidou constellation. So we can use all of this data to do precise positioning, and we can have more robust and even more precise positioning results from this from so many satellites. And the observations from IGS stations can be transmitted back to the IGS data center with the lowest possible delay, and typically within several hours. For example, for daily data, within 24 hours, we can receive the use the 30-second interval data to do daily analysis. We can use the higher data within which can be delayed by about a few hours. This is the introduction about the IGS data center, which we may be familiar with. So whenever we wanted to use some example data, we always go to the IGS data center to download some example data for free of charge, and we can do some analysis. We can test our software. We can do some exemplary data analysis here. The IGS data centers are divided into 3 categories. So we can have the global center, which now we have 6 global centers. Like the one is in China, and the others are in France and Korea. They have the full capacity to store the global network data over the past 3 decades. Okay, this data will be provided to the analysis centers now, which are shown here. The IGS Analysis Center, whose short name is AC, they are responsible for processing the data provided by the DC to deliver the GNSS products. So these GNSS products include the orbits and the clocks, as well as the ERP, the Earth rotation parameters, and the Troposphere products, as well as such kind of phase-bias products here. The phase-bias products are very critical to the ambiguity resolution at a single station, which is enabled in PPP. We don't use any double differencing technique, and we use only the data from a single station to recover the integer property of ambiguities. So this is very hard work, but fortunately, we have the phase-bias products from the IGS here. So now we have many more stations and many more ACs to provide this kind of product over nearly all frequencies. So the usual frequencies, for example, the L1 and L2 from GPS, and the E1 and E5A from the Galileo constellations. So from this, using this phase-bias product, we can separate the integer property from the errors that we don't like. The IGS products can be divided into several categories in several lines. For example, the ultra rapid, which has a latency of about 3 to 9 hours. And this ultra rapid product can have a prediction path of the next 12 hours, so which can be used to do real-time positioning. So actually, in the industrial applications, all of the real-time orbit are actually predicted orbits. So they are based on the technique provided by the IGS to have this kind of real-time high precision PPP service to be available to the, for example, the self-driving vehicles. And we have rapid lines and final lines. They are the final lines are the most precise products, and they can be used to analyze the global constellation evolution, as well as the ground network analysis to monitor the cross-transformation and the global reference frame establishment. And this shows the file names of the IGS products. You can see here, because we are going to mention a lot repeatedly the files that are going to be used by our software. So for example, the RANEX file, we use the RANEX file, which contains the raw observations, such as the super range observations and the curve phase observations. So these observations are contained in the RANEX file, and it has a definite format description. So you need to be familiar with this, because we're not going to have a detailed introduction of the RANEX file format. And then we have the precise ephemeris, which is called SP3 file. And this is a format defined by the IGS to contain the tabulated positions of the satellites. For example, for every 15 minutes for GPS and every 5 minutes for the Galileo constellations to allow for the precise description of the E14 and the E18 satellites in the ellipse orbits. So we use SP3 precise ephemeris to which are critical to the PPP AR software. And then we have the precise clock product, which is contained in the clock RANX file. We call it the Synix as well. So we are going to have a new format for the Synix file in the future, which will contain some more information like the phase bias information in the header of this format. And then we have the ERP, which is short for the Earth rotation parameters. And these ERP products are used to maintain the connection between the terrestrial reference frame and the celestial reference frame. This can help us to have a more precise computation of the loading effects, because in the celestial reference frame or in the inertial reference frame, we can have a more precise description of the theories from the IERS conventions. And then we have the APC antenna phase center described in the NTEX file. So this is the NTEX. The NTEX file is defined by the IGS as well. So it contains all kinds of satellite antennas and all kinds of receiver antennas. It will describe both the phase center offset and the phase center variations. So the phase center variations will depend on the azimuth angle and as well as elevation angle of the satellites with respect to this this antenna. And then we have the TC grid. TC means total electron content, which describes the ionosphere delays over the path between the satellites and the receivers. And this kind of products are produced by the IGS as well, and it can it is named as the Ionics file. So the Ionics file contain the graded tag values, and which can be used to model the higher order ionosphere delays. And this kind of delays can be corrected in our software as well. But we have to use the Ionics product. And then we have the bias Synix file, which contains the signal bias, including the code bias and phase bias. We call it the bias Synix file products in our software, and this can be obtained from the IGS repository. And then we have the Orbix file. The Orbix file contains the satellite attitude, which describes how the satellites rotate itself around its radial direction in the space. So this correction is very critical to the correction of the antenna phase centers and as well as the clocks. So we use this Orbix file from the IGS to have a more precise description of the satellite attitude in the space. Okay, that's all I have. And so any question on this part of the material? So we just have very brief introduction, and there are some actually there are some kind of breaks in the continuity of the slides, because we just ignore some of the necessary knowledges before we can understand each part of this slides. Actually, we don't have enough time to make a very detailed description of the GNSS techniques. We just picked a little bit from the pool of the GNSS knowledge to enlighten everybody here, and to make you familiar with some basics of the products of the data that are going to be used by our private PPVR software. All right, anybody who has questions on this? Let me see. So there is a question about the reference frame of each constellation. So of course, yeah, from the if you are going to use the broadcast ephemeris from each constellation, for example, the GPS broadcast ephemeris, and and Galileo ephemeris. These two systems have clearly different reference frames. So you cannot directly use them to do the positioning, especially in the standard point positioning. You have to make some kind of a transformation, and these parameters are actually provided by the broadcast ephemeris. You can do the transformation here before you can have a combined integrated solution based on multiple constellations. But in the precise point positioning, we are not going to use the broadcast ephemeris to enable high precision solutions. So we are going to use the products provided by the IGS, the precise orbits and precise clocks. The precise orbits from multiple constellations are actually expressed in the same reference frame. That is the IGS 14 or IGS 2020, which is going to be released in the near future. So, in the SP3 files, all of the constellations are expressed in the same reference frame. So we don't need to worry anything about this reference frame incompatibility. You just needed to download the SP3 files and then to run the software, and you can have the final solution to be in the same reference frame as the IGS 14. All right. The second question: what is the difference between the PPAR, product PPAR, and the IGS PPAR working group? Actually, there are two different things. The product PPAR is a software, is an open source software that you can use to do positioning at a single station, to calculate the troposphere delays at a single station as well. And IGS PPAR working group is an organization under the IGS to coordinate the generation of the phase-wise products. And at the moment, I'm the chair of this working group. So we are paying much attention to each AC of IGS to encourage them to provide a multi-constellation and multi-frequency phase-wise products to benefit the third-party users, and to encourage the users to use PPAR techniques to do their science analysis and some other applications. All right. The third question is that if the software uses precise orbit and clocks, that does mean that it is not designed for real-time analysis. Is this correct? This software is not for real-time applications. We use only post-processed orbits and clock and phase-wise products to do PPP analysis. If you wanted to do some real-time analysis, you have to use some other software. And usually this kind of real-time software are not so open source, because they can also be used by the industry to enable vehicle navigation and pedestrian navigation as well. So I don't think you can find a lot of open source real-time PPP software. But for most of the users for science research, I think post-processing can be enough. This will take care of the different coordinate system, about different time system. In the sequence file, in the clock file of the provided by the IGS, the clock file also contains all of the constellations, so you don't need to worry about anything about the time system difference. All of the time datum has been aligned with the GPS timescale. So after you have your positions available, that position is with respect to the GPS timescale. How long it takes to process a single station with all listed products? That is for the time. That depends on the duration of your data. If you have only one day data with a sampling rate of 30 seconds, that only costs a few minutes, 1 to 2 minutes, because we have several iterations before we can achieve the final solutions. So normally 1 to 2 minutes for a 30 second daily data to be processed for one station. And if you have higher data like the 1 Hz data or even 50 Hz data, that will take a long time. For example, for 24-hour 1 Hz data, that will take a few tens of minutes before you can finish the processing. So so that depends on the data duration. It isn't supported by Pride. Didn't get that from last slide. It is what it is. The SP3 is supported by the Pride. We don't use any other format of the precise orbits orbit product. We just use the Igs standards to do our PPP processing. So we can use, whenever you can download any product from the Igs, we can always accept it in our software, and it can use that kind of Igs product smoothly without any problems. Can one use the software for processing data from receivers that were not calibrated? No antex input. You mean without any antenna calibration, so you can use the software to process that? If this is what you mean, for some low-cost receivers, because of the antenna, because of the antenna definition is not present in the antex file, we can still process it, but the antenna offset and antenna phase center variations will be set 0 in your final solution. So actually, what you got from your processing with low-cost receivers and the low-cost antennas will be respect to your phase centers rather than with respect to your your antenna reference point. So you have to make sure that what you've got is actually the position of your phase center rather than any ground mark of your stations. Right. Well, I missed your answer to the question to the software used for real time. No, this software cannot be used for real-time analysis. It's a post-processing software. We are going to, there's the story. We are going to provide an open source real-time software, which is combined with the BNC software provided by BKG. The BNC software cannot resolve the ambiguities, from my understanding, and we can improve its stability. But this software is going to be used for, the open source software based on BNC, and we are going to improve its capability in monitoring the ionosphere as well for the tsunami monitoring. So from our new software based on BNC, we can produce the positioning displacement, real-time displacement time series of a tracking station, as well as the ionosphere disturbances caused by a mass redistribution of the water caused by some kind of tsunami hazards. So in this case, we can, but that cannot happen before the end of this year. We can release this software in the next year, but it is still undecided. We have some problems for the development of the software. So let's see what will happen in the next year for the real-time PPPAR software based on Pride group, right? How do you compare Pride solutions with an MPPAR solution? I myself don't do any comparison between the Pride solution and the NRCan or opposite solutions. I read some papers. I think I saw some papers for the comparison. You can refer to some other papers on this, right? And this comparison should be based on the same products to be used. For example, if you wanted to compare two different software packages, you have to use the same products, same orbit and same clocks. So same orbit and clocks from a third party, from IGS or from code. And then you can compare their performance and that will depend on the quality control measures of your software. Sometimes for some really bad data, if you have done the robust measures to take care of the outliers and cycle slips, then your software cannot do a good job. So that needs to pay attention. That needs to be taken into account before you do a reasonable comparison. Okay, Melissa, I think we have finished this part.
Okay.
And I don't see any further questions here. So shall we have a break, or we just continue?
Quick break probably would be good, like a 5-minute.
Okay, we can have a 5 minutes break, and then we come back to continue our next talk on the introduction of the installation of the software. Okay. So let's see you in 5 minutes, and we come back in 5 minutes. All right, let's start here. Let's see.
Okay, everyone, can you hear me?
Yes, I can. We just have a break of 5 minutes, so we can come back in 5 minutes. Hi, Jihan. Could you start to share your screen?
Oh yes. I'm trying to do. That's fine. Can you see the screen?
Yes. No, we can't. I can't see anything from your screen.
Oh.
There
You
should be,
haven't shared.
I was gonna say there should be a share screen. Oh, okay, now we see some slides.
Okay, got it.
Oh, thanks.
Okay, yeah.
Hello everyone. I'm Lindsay Han from the Pi Lab in the GNSS Research Center of Wuhan University. This is the second of our 3 classes today, and I expect to spend half an hour giving you a basic overview of the software PPP AR. Some of you may have attended our numerical course in the last year, but it has been a year since then, and our software has been greatly improved, both in terms of functionality and in the ways it is used. That I felt it is necessary to start by introduce these new features and updates. The PPP AR released in the last year is known as version 2.1. This version supports the basic functions such as the multi-GNSS processing with GPS, GNSS, Galileo, Vrdm, and QZSS. The undifferenced ambiguity resolution and the rapid PPP AR service from Wuhan University. These basic functions enable you to simply but effectively process your GNSS observations and achieve the PPP AR. Then, in April of this year, we released the version 2.2 of PPP AR, including an easy-to-use graphic user interface and a brand new command line interface, multi-day processing, and the near real-time PPP service. In the course that follows, we will show you how to choose and how to use these functions and features. Next, we come to the command line interface of the new version of PPP AR. We have completely redesigned the usage of the PPP command. So now we no longer need to enter a long list of options to process the observation file. You just need to input this file after the PPP, and this script will fill in the options automatically, just like the first command line we show here. And if you need to custom the processing mode instead of applying the default setting, you can refer to the help information and input the corresponding options and arguments. In the second command line, the option M is used for specify the positioning mode, and the argument S is following the option is short for static. The option S and E define the processing time of multiple days, and the program will search for the next observation file automatically. The third way to specify your configurations is to input a configuration file after the option CFG. The configuration file we used here is basically the same as the one we used in the former versions. All command options can also be set in the configuration file. You can set your frequently used options in this way, and the command line can be more concise. Of course, this file can be used together with the other command line options, and the options in the command line, such as here, will overwrite their corresponding settings in the configuration file. In general, the priority of the different ways to use the command line interface is the command line options, the configuration files, and finally the default settings. In comparison, the graphical user interface is much simpler in operation, but some advanced features are disabled in the GUI version. In general, the functions of the GUI for both Mac OS and Windows users are similar to the version 2.1 we released in the last year. Although most of the basic functions, such as the multi-GNSS processing, the high-rate processing with a sampling rate up to 1 Hz, are remained. The latest features, including multi-day processing and near real-time service, are available for the GUI version. Next, let's turn to the software package and look at the directory structure. There are 3 documents, 7 folders, and 1 installation script here. The document gives some information about the update history, the general public license, and an overview of the software. The installation script is marked as green, and we can see the suffix of the script is .sh, which means it is written in bash. You should execute this script to finish your installation. As for the folders, you may not find the bin folder at first in the software package, but it will appear after you successfully installed the program, and it stores all the executable programs we used. The doc folder holds the menus that you can refer to when you encounter problems. The example folder holds some data, and you can use them to learn the basic usage of PTP3 command. Some of this data will be used in the later classes too. And the test.sh script is contained here. You may execute this script to finish the test process. The other folders host the files as their name suggests, such as the installation package of GUI, the scripts, and the source code, and the table files. The newly presented folder bin contains all executable programs used to complete processing tasks. Some of them perform the major computation tasks in the processing flow, such as the RSig for ambiguity resolution and the LSQ for least square estimation. Others, like the get control, PBO pose, and the XYZ to ENU, are not involved in the processing flow. They are used to deliver the configuration or help analyzing the processing results. The usage of these utils will be introduced in the later course too. The scripts here are in the scripts folder. The most important one is the PTP3. This is the main script we use to interpret the command line, check the configuration, and manage the processing flow. Note that there are 2 scripts named with PTP3. One is for the common Unix system, and one is for the Mac operation system. They are slightly different in bash syntax. Usually, you don't need to worry about how to choose between these 2 scripts, as this can be done automatically during the installation. Then, after the installation, one of these 2 scripts will be renamed to PTP3, which is exactly the command we used to finish our processing. The merge to Vrdm is used to merge GPS and GLONASS broadcast navigation files into one file in case you have no multi-GNSS navigation file for your data processing. The other scripts are used to visualize the results from PPP-AR. Not only the processing results, but also the residuals, the zenith tropospheric delays, as well as the satellite numbers, and so on. The plotting scripts are written in Python shell or GMT, and they are with the suffix .py and .sh respectively. Then here is the source code. The codes for the programs in the bin folder are roughly grouped by their names into the several folders appear here. For example, we can also find a folder named as RSig and another folder named as LSQ here. Apart from that, there is a header folder containing the header files that define the constants and the data structures, and a lib folder containing the common used library functions. Then we come to the table files. There are some files that used to define the names of the resource files, such as the file name, and the grid files for calculating the tropospheric corrections, and the ocean noding coefficients, ocean node, and the antenna phase center model in the index files. They are used to calculate the different corrections for the least square estimation. Usually, we don't need to modify them. They can also be updated automatically. Okay, that's all for the first part of this class, and I will introduce further about the processing procedures of this software in the second part. First, let's look at the green box in the lower left and take the commands as an example. After you execute the PTP3 command to process the observation file, the PTP3 script will do the parsing and the checking work, then create the necessary directories. There will be a new folder shown immediately in the directory where you execute this command. So we will find a year folder named as 2020 here. In this year folder is a day folder named as 001 and a product folder. We call this day folder as the working directory because all temporary files and the results will be put here. The product folder is used to store the products, and the path to the products can be customized by yourself in the configuration file. Then, after creating the directories, the PTP3 script will continue to check all the required data and products are in the directories where they should be. Otherwise, it will try downloading this data and products from the remote server. The required data besides observations is the broadcast navigation files. The type of navigation file can be either BRDC or the BRDM, but they will both be renamed to BRDM in the lower cases and the short naming convention for ease of processing. It will be put in the data directory, namely the same data with the observations. The default products we used are the rapid products from the Wuhan University. By now, they are unavailable at the common Igs data centers and can only be downloaded from the FTP server at the Wuhan University. These products are the precise orbit, SP3, the precise clocks, CLK, the Earth rotation parameters, ERP, the attitude quaternions, OBX, namely in the OBX format, and the signal biases, BIA. They will be moved into the products directories after the downloading is finished. After the preparation of environment and files, next, we will enter the main processing flow of Pride PPP-AR. The processing flow consists of 4 parts, organized from the left to the right, and they are connected by the arrows. The preparation of initial coordinates and orbit files is the preparation step. Then is the preprocessing of the observations, follows the parameter estimation and the data cleaning, and finally, the ambiguity resolution. We'll look at every part in detail and see what data are input, how they are processed, and what results will come out. The first programs to be run are the SPP and the SP3 ORB. SPP is short for the standard point positioning we just introduced before. The observation file and the navigation file will be input to perform epoch-wise positioning. During this rapid and cross-processing, the time range of the available observations can be defined, and the initial coordinates can be obtained. Another individual task is performed by the SP-Shape ORB. As the name suggests, this program converts the SP-Shape file to the self-defined ORB file. The ephemeris for each satellite will be interpolated, and their coordinates will be converted to the initial system, which is more convenient for calculating the related corrections. Following is the data preprocessing with the TEDIT program. The TEDIT is named after the table edit algorithm originated from the Gypsy. This algorithm is commonly used in the health diagnosis and the quality control of the GNSS observations. It has been modified for many times since its first appearance. We used this program to identify the bad observations, detect the cycle slips, the clock jumps, as well as the other anomalies. Another task performed by TEDIT is to identify the continuous phase observations, which may be interrupted due to the circle slips or the other factors, or independent continuous observations correspond to an ambiguity parameter. These ambiguities will be written into the log file along with the other text. Now what we see is the header of a log file. The ambiguity is labeled as A and B. They are listed in the block of their beginning epoch as this upper red frame surrounds, and the ending epoch of this ambiguity parameter is listed in the right. The tag DEL means the tagged satellite is deleted in this epoch. As the yellow frames run, the suffix gives the reasons about why they are deleted, such as the low because their elevation is too low in this epoch, or because they are in a short observations session and they have not enough observations in this epoch. The records in the header are surrounded by the blue frames are a statistic of the overall quality of the observation data. Then now we come to the most important module of the processing flow, the LSQ for the least square estimation. This program with all files we prepared for the GNSS processing, such as the observation data, the products, the table files, as well as the initial coordinates, and the log file we just generated. The files we listed here is just a part of the all necessary files for the LSQ. The corrections calculated from these files are involved in the same adjustment system with the observation data. The parameters are estimated to form the solutions we need, and without the integer ambiguity constraint, we call this solution as the float solutions. The parameters to be estimated are the phase ambiguities, the coordinates, the receiver clocks for each constellation. Note that the intersystem biases have been merged into the clock. That's why we should estimate separate clocks for each GNSS system. Besides, there are the zenith tropospheric delay and the horizontal tropospheric gradient. We call these two parameters as the ZTD and HTG, and there are two components of the tropospheric delay. Now we have noticed that there is no parameter on the ionospheric delay. This is because we have combined the dual frequency code and phase observations to form the ionosphere sphere-free combination, which is well known and commonly used for the processing of GNSS data. This linear combination takes advantage of a property of the ionospheric delay. Let's look at the equation. The P and L here are the code and phase observations, while this A is the major component of the ionospheric delay. And we have known in the classes before, this is exactly the first order ionospheric delay. We can see it is inversely proportional to the square of the frequency. Thus, by the ratios alpha and beta, we can construct a linear combination of P and L that maintains the geometric items but completely eliminates the ionospheric delays. This combination is necessary for us to isolate the effect from the ionosphere because they are hard to be estimated or corrected but may reach hundreds of meters. As for the least square estimation, we apply the parameter elimination methods proposed by Professor Ge to accelerate the process. The most important feature of this method is to reduce the size of the normal matrix, so that the complexity of matrix inversion can be significantly reduced. After inverting the normal matrix, we will recover the eliminated parameters, but not their covariance. It can also reduce the computational burden, and we usually do not test covariance. In contrast, parameters with useful covariance will be remained, typically the coordinates and sometimes the ambiguities. The next step after adjustment is the data cleaning. The Vrdm program, which is short for the residual diagnosis, will read the residual file in the float solutions output from the LSQ, and further identify the outliers and cycle sleeps. Then the log file will be updated by this new diagnosis. Such a post hoc diagnosis is necessary because it is obviously more precise than the preprocessing in the TEDIT program, which performed without precise corrections. To maximize the quality of the fault solution, the loop consisting of LSQ and Vrdm will be executed for at least 3 times until no more observations are removed and no more ambiguities are inserted. After each Vrdm run, we can see the output like this. The arguments of Vrdm are the threshold values to determine the cycle sleeps and short ambiguities. They are in units of millimeters and epoch number. The threshold for the circle sleeps and outliers will gradually reduce from 400 millimeters to 50, so that we will not remove too much observations at once. This table shows the RMS residuals of each satellite, and there will be a statistics about how much the removed observations and the inserted ambiguities are, and what percentage they are account for. This is the output from the last Vrdm. We can see the threshold here has been declined to 15 at T, and there is no more observations or ambiguities changed. The RMS residuals have been reduced a lot, and most of them are around 1,000 millimeters, while the maximum one is the 24 from the R11 and the G03. Now we can consider the float solution has been fully refined because there is no more necessary to remove the observations and insert ambiguities, and we can just try to fix the float ambiguities now. We have known there are many prerequisites for solving the ambiguities. That is why we have so complex processing flow before the ambiguity resolution. Most of them are used to maximize the success rate. However, the procedure may seem quite simple here. The RC program reads the ambiguities from the AMB file and then fix the float ambiguities to integers. These fixed integers are written into the CSV file. With the CSV file, the covariance between the parameters can be reduced, so a higher precision of the estimates can be achieved in the fixed solutions. There is an illustration about how ambiguities are organized and how they are finally resolved. The ambiguities are denoted as N here, and the biases are denoted as B. The subscript R and the superscript S represent the satellite, the receiver and the satellites respectively. Most of these procedures are accomplished in the LSQ, and only the final resolution is performed in the RC. We first apply the satellite signal bias corrections from the bias product, so only the receiver biases are remained here. Then these row ambiguities are combined to form the ionosphere-free combination along with the observations. These ionosphere-free ambiguities are labeled as IF here. However, these ambiguities cannot be solved to integers directly because they cannot be represented as integer multiple of N1 and N2. So we will form another linear combination called the Melbourne-Banner combination to form the wide length ambiguities. The wide length ambiguities are first resolved, then you can help decomposing the ionosphere-free ambiguities to the narrow length ambiguities, and then you solve them. You don't need to worry about these unfamiliar names. The only thing you need to remember is that the solved wide length ambiguities are the prerequisite to resolve the narrow length ambiguities. In this process, the satellite biases are corrected by the bias product, and the receiver biases are eliminated by the satellite difference. The undifferenced ionosphere-free and wide-length ambiguities are stored in the AMB file, and we can see they are still far from their integers because of their receiver biases. After the satellite differencing, the receiver biases can be eliminated, and the ambiguities are resolved into the set file as we show here. The left column is the wide length ambiguities, and the right column is the narrow length ambiguities. All are integers instead of the float numbers. The statistics about ambiguity fixing rates will show up the RC round, and we will see the number of each type of the ambiguities, and the wide length and narrow length fixing rates. Note that the narrow length fixing rate is given respect to the wide length because we have said that the narrow length ambiguities can be resolved only with the wide length ambiguities resolved. The statistics are given separately for each constellation. It is because the receiver bias may be different from signals to signals transmitted by different GNSS. For this reason, the second and third generations of Beidou are considered as two constellations here because they are transmitting two different signal structures. Normally, the fixing rates of the wide length can be higher than 90%, and the narrow length should be higher than 80%. especially under the good observation condition here. While more ambiguities are fixed, the precision of the fixed solutions can be higher. So you can try to adjust your processing strategies to maximize the fixing rates. And this will be introduced in the following classes. And that's all about our second class. We have finished the introduction to the features and the processing flows of the PPP AR. Now, if you have any questions, you can open the microphone or send me your questions in the channel and snails, and we will try giving the answers. Thank you for your attention, and that's all.
All right. Thank you, Jihang. Anyone who has any questions for Jihang for this part? This is actually the introduction for the software structure and the executables included in the software. So you can use these slides as some kind of check table to see the functions of each module within the software. When we leave the single choice, the fails when we use manipulated I don't understand what you mean here, the Roberts, and what do you mean by manipulated observation files? You mean to you change the files by hand, or more about stylus? Yes, Antonio, we can use both format 2 and 3, Redux 2 and 3, both can be recognized. It is such a reparation made in the different. Alex, it is actually the difference between the same observable coming from two different satellites in the same constellation, from GPS to GPS and the Galileo to Galileo satellites. Robert, as you can understand, how did you add it to the files using what software? You mean to change the format of the Redux file, or if it is in a Redux 2 or 3 standard format, I think we can recognize the file using the software. And you said you left the signals of choice to process. What do you mean by signals of choice? You mean use some two different signals? You don't use L1 and L2, but use L1 and L5, or just in this case? If we don't have any further question on this, we can move on to the next speaker by Zheng Jing, who is going to talk about the installation of the software, and then we can see whether this can help Roberts of the processing. Zheng Jing, could you share your slide, share your screen?
Okay, can you hear me?
Yes, I can.
Oh, thanks.
Right.
Hello, everyone. I'm Zheng Jin from the Private Lab, and I will talk about the third class. After a general understanding of the PPP principle and create the PPP AR software, let's learn how to install and run the software next. At the end of the course, we assigned 2 homework. You can try to install and run the homework yourself. First of all, let me briefly introduce the basics of the Linux terminal related to the software operation, which mainly include commanders and scripts. Commanders are a series of system keywords that are used to achieve different functions, include MV, ls, cat, and vi, etc. Enter the appropriate commander and corresponding options into the terminal to make it work. And the scripts are executable programs written in scripting languages such as Shell and Python, and require specific and interpreter or executable permissions to run. For the installation of CLI version, make sure you have the required system software on your computer. For example,
Hi,
Bash.
Hi, Zhengjun, sorry for interruption. Could you play your slides?
Yes.
Okay, good.
For example, Bash is the interpreter needed for shell Bash scripts. The function and make are for compilation, and the Python plotting scripts require the NewPin module and the matplotlib module to be installed in advance. After preparing the software package and the base system, run the install script to complete the compilation and installation, such as under the software directory, run the install script from the terminal. You can enter bash install.sh to install the software, or you can give the executable permission to the script and run it by .install.sh. Sorry. The installation are divided into 3 steps. First, compile and generate the executable programs for each module. For example, here is to compile the SPP source code and generate an executable file. Then copy the executable file and the script to the installation directory. The installation directory is a hidden directory under home directory, i.e. .pred _PPAR _bin. Finally, write the installation directory path to the environment variable. This way, you can call the software from any directory. The environment variables will be written to the .bash_rc file in the home directory under Linux system, and .bash_profile for Mac system. When this logo of PPPAR is displayed, it indicates that the installation is complete. For novice user, it is recommended that you enter Y to run the example to verify that the software installation is valid. I want to run the test example here You can try it yourself later. And in addition, not install software in the root directory due to permission issues. After running the example, you can compare the example results with the reference results to further verify the validity of the software installation under the example directory. Those five examples contain 3 position modes and 2 ambiguity resolution modes. Ambiguity resolution methods including rounding method and lambda method. The rounding method is used when the time period is long and the float ambiguity is highly precise. Lambda method is used for short time periods by transforming the convergence matrix to achieve the effect of decorrelation and then obtain the integrate ambiguity. So it is not necessary to use the lambda method when dealing with long-time data, but it will lead to low efficiency or even running field. Long period and short periods are divided into the CLI software with a threshold of 6 hours. The GUI version is divided into Windows version and Mac version. Windows version is installed through .exe installation method, and Mac version can be used after unzip. The GUI directory in the software package holds the GUI version. I'll show you how to install the Windows version. Click the exe and select accept the agreement and click next. Select the installation directory or use the default installation directory. Be careful, do not install the software in program files directory on the C drive. And then click next. You can choose create a desktop shortcut or note and click next. Click install. And finally click finish. Here we are. The Windows version is successfully installed. Let's move on. When using the software for data processing, the CLI version and the GUI version are roughly the same. You need to prepare your own Unix observation fields, and the external fields need to be prepared when not collected. And the third step to update the optional table field, you can find it in the section 5.4.3 of the user manual. The difference in usage between the CLI version and the GUI version are: the GUI version requires Unix observation fields to confirm the standard naming format. When using the CLI version for multi-day processing, if there are multiple observation fields, those fields should also conform to the standard naming format. And the CLI version specific data processing strategies via command line parameters and configuration field. The GUI version specific data processing strategies via interface or configuration field. The CLI version invokes the PPP3 batch split for data processing, and the specific solution strategy via command line parameters. You can enter PPP You can enter PPP3 in the terminal. You can see the meaning of the corresponding commander parameter and their options. The meaning of each parameters will be introduced in subsequent course. And the 5 instances of the example directory are into 3 position modes, static, climatic, and fixed, and specific by the happen M parameter. The static mode estimates a set of station coordinates during the processing time, and the climatic mode with a set of station coordinates estimated for each epoch in the processing time, and fixed mode fixing the station coordinates to the coordinates in the RGS daily things field to improve the accuracy of ZTD estimation. So F mode can only be used for the RGS stations. Note that the last parameter of PPP3 needs to be the observation field. The result directory of the CLI version is the year directory, and by default, the product directory is also located in the year directory. The dev year directory is a directory where the data is processed by the software, and the result fields are stored in this folder. The naming format of the final result field's name is 3-letter prefix underline for digital year and 3 digital dev year underline and 4-letter station name. The product directory is divided into 4 subdirectories. The common directory stores the process product include satellite orbit, satellite clock, Earth rotation parameter, satellite altitude, and signal bias product. The ION directory stores the GIM products required for high order ION spherical corrections. The VMF directory stores the grid field required for the VMF1 or VMF3 ZTD mapping functions. The SSC directory stores things field for extracting station coordinates in the F mode. The GR version uses an interface to select the observation field and modify configuration for data processing. The observation field must conform to the standard naming format. Note that the GR version does not modify the corresponding processing strategy based on position mode or other information. So you need to pay attention to whether the configuration is corrected when using the GI version. The method of modifying configuration information in the GI version can be found in the user menu, and we will describe it in the next lesson. The results directory generated by GI version is at the same directory as the rings observation field. Unlike the CLI version, the GI version will only keep the final result fields, and all other fields will be deleted. And the Levy folder stores the broadcast if size, and the product directory stores the required process product. This is the first homework of this lesson, using the CLI version to perform calculations for the 3-position model. Switch to the example directory and use CCG2 or 110 days in 2021 as the example data to prevent result overwriting. Rename the result directory after each calculation. I will show the first example. Change the directory to the example directory and enter the commander pg_send data 2021. And don't forget the option server parameter. And run it. When the program is running, the screen will output the corresponding messages, indicate which step the program has reached and the corresponding result. After running, you can view the result under the year directory. Corresponding to the screen output information, the corresponding to the screen output information, the overall optional flow of the software can be divided into 3 parts: data preparation and processing, last square estimation and data clean. And the third part is integrate ambiguity resolution. In the first part, first prepare the required external fields, include partial table fields, ground case emphasize, and precise product. Secondly, the elevation coordinates of the station are calculated by SPP. In F mode, extract the coordinates in the sinus field and the elevation coordinates. Next, TDIT will processing the observation data, detect the cycle jump, and remove the outliers. In the second part, LSQ is the last square estimator that estimates parameters and generates most of the result fields. And Redig performs residue editing based on residue field output by LSQ to identify some small cycle jumps and remove outliers. LSQ and Redig will iterate until the data is cleaned up and then go to the float solution. In the inter-ambiguity resolution part, async outputs the corresponding ambiguity resolution related information, include float ambiguity related information, satellites for single difference, and float ambiguity and its STD for wide line and narrow line ambiguity respectively, and a period of single difference ambiguity and a fixed flag. The integrate rounding part is the fixed rate of rounding method, include the number of fixed narrow ambiguity, the number of fixed wide line ambiguity, and the number of all single difference ambiguity. If the ambiguity resolution method is the lambda method, async will also output ambiguity resolution information about the lambda method. After the async run is completed, the fixed solution is available in next LSQ. This is the second homework of this lesson. The GUI version can also use the CCG2 station for practice. Let's try to use the GUI version to calculate. I put the observation field in the homework directory on my desktop. Click on this icon to select the place where the observation field is located. Select the desktop and homework directory. And select CCG2 observation field. You should modify the options dialog after import the observation field ended. Here we use the default configuration and click on execute. The screen output of the GUI version is the same as that of the CLI version. Considering the time, download the external field in advance. So when you run in the software, you probably need to download the external fields. After the calculation is completed, you can click on the plot interface for plotting figures. Click plot and click plot figure to open the plotting window. The result fields that can be imported include key field, RES field, and ZTD field, such as import key to plot the results of the key field. Include position time series and positioning trajectory and PDOF and satellite number. And click import RES to plot results related to the RES field. Include ionious free observation residue and sky view. And click import ZTD to plot ZTD time series. In the menu bar, you can also select the color and the line width and font style or the font size. For some picture, such as residue time series, you can also select which GNSS system or which satellite is displayed. In addition, you can also click field and click save current figure to save the picture. And we will info you of the details of the homework through the Slack, and some of the steps and results about the homework. We will explain it in the next lesson. You can give feedback via email if you have any question. Thank you. That's all.
Okay, thank you, Zhengjing. Does anyone have any questions for this installation and the first trial of the software? I can see a lot of questions in the chat box, and actually people are very concerned with the problems of the private software. I think the most common one is that whenever sometimes you needed to use some other frequency combinations. As we have said in our slides, we need dual frequency data to enable PPP AR, and single frequency data cannot be handled by this software. And for dual frequency data, you have to use the pre-required frequency choices we have made in the software. For example, for GPS, that must be L1 and L2. And for BDS, you have to use the B1I and B3I rather than any other frequency combinations. So that's why you see a lot of problems when you are using some kind of signals that are unusual in the common network analysis. But we are going to release a new version before the end of this year, and we actually already have that version in our pocket. The problem is we are confirming the multi-frequency phase bias products. We are doing some additional check on that base byproduct before we can release this new version, because we want to enable all frequency PPPR. That means you can use any frequency combination to enable ambiguity resolution at a single station. That will be very helpful and interesting and beneficial to some people. So that's why we are waiting. But actually, that version is already. The problem is that we need to make the products, the multi-frequency based products, available to everyone in the near future. Okay, we have some messages from the chat box that was meant for public. What's this? So, do we need to download both GUI and CLI versions for the homeworks? I don't know. Zhengjing, do you mean you have to? The homework has to be done by using the GUI version or CLI version?
You can choose one of the software and your requirement.
Yeah, you can choose anyone. You can choose anything to process the data. I myself don't recommend the GUI version, no matter whether it's a Windows version or Mac version, because we have tried a lot to develop these two kind of GUI versions, and it costs a lot of time of us. It's just because some students, some international students, that wanted to teach the software in their class, and they don't like the command line version, and so we developed this kind of version for the very junior users, and but we make some limitation on the function of the GUI version, because the Windows version cannot accommodate the very high rate data processing. It is always crashed because of the 50 Hz data, because we cannot have a so large an array to be allocated in the runtime. And the Mac version also has the problem, because we tried to make an installation of that Mac version, but that will cause some contradiction with the system security checks of the Mac system. So some people may not use the Mac GUI version. It has some problems, but then the CLI version can be fine, except for some cases in the Mac environment, because the Mac terminal has a lot of differences from the Linux terminals. For example, for the GUK, AWK, for that work function, the grammar of the work function in the Mac are quite different from that of the Linux version. So we have a lot of such problems to make some accommodation. And but you know, in China, we rarely use the Mac operational system. We really like to use Windows or Linux version. So that sometimes we needed to find someone to be familiar with the Mac terminals and the Mac grammars. And that's different from the case in North America. You know, when I was in North America, we always use Mac. So now you can see in my I use Mac. I still use Mac in my office, and I'm the only one in my department to use Mac computers. And so there is no Linux GUI version. It doesn't make sense to make a Linux GUI version. It's not necessary. Because the Linux GUI version is even more difficult to develop, and yeah, the slides will be available later. I think Melissa will release the slides later. We are okay for the release of the slides. So it's no problem. What would happen if we use data from a station that is non-Igs station with software with the matching of the receive and attending events in their products? Yes, if you use a station from the network outside the Igs reference stations, and then you can still use our software to process it. There is no limitation for you to process any kind of data. When you the software will read the header information from the RANX file, including the receiver and the antenna information. If you have the correct format of the RANX file and have the correct antenna information, the software will automatically match the antenna information in the header of RANX. with the n-text file. So if you can't find the correct item in the n-text file, then the antenna offset will be set to 0, and the processing will go on without introducing the PCO corrections. So so you have to make sure your head information is correct. Then I download the reversion. I use random file with Beidou's. Yeah, you can process all Beidou satellites, but you have to use the C2 and C6 signals instead. We will link in the details of how it works. All right. Okay. Other than the important thing, right? Jihan, do we still have many kinds of configuration file for the software, or we just only one model file, right? Configuration file.
Right. Here we just put a single configuration template in the table folder, and we have no the other configuration files. But you can find some of these configuration file for different processing purpose in the earlier versions of PPP AR. Because when you apply the default settings, we think our default settings is suitable for most of the common situations.
Yeah, last year when I made the first training class alone, we used different configuration files to enable, for example, the static processing, the kinematic processing, the seismic data processing. But now we just get rid of that configuration because we had a lot of complaints on this, and we just want to make our software to be more friendly to everyone. So we use the command line instead to have all kinds of options to be available to the users. So you can use the options to process any kind of scenarios of data processing, for example, of kinematic data processing, the hybrid data processing, and even for mobile platforms like the airplanes and the ships. So then you don't need to worry about any configuration file, and the configuration file will be automatically generated according to your option choice in a command line. I think it's if you don't have any question, we can meet each other. All right, can you repeat this thing? For GPS, it's L1 and L2. We support the most conventional signal combination, which, for example, the GPS L1 and L2 supported, and for Galileo, it's E1 and E5A. And for GLONASS is G1 and G2, and for Beidou is B1I and B3I. For Beidou 2 is B1 and B3I as well. And then for QZSS it's L1 and L2. So that's the signal combination we support at the moment. But then that case will be changed soon, and we can support any combination of choices. Just like the Robert says, the signals of choice. So you can use the GFC Renix to add it to the Renix file for any frequency choice, and then we can support each combination and enable the ambiguity resolution based on any combination of choices, combination of signals. Right. So if you don't have any question, right. So I have a question about the log file. For the cutoff angle, it is based on the cutoff angle, and it is automatically checked by the software. So it's not an average cutoff angle. It's just an angle set 7 degrees or 10 degrees, and for each epoch of observations. So we will compare the elevations of each satellite with the cutoff angle. If it is lower than the cutoff angle, then the data will be masked or removed from the data from the Redux file. I mean from the Redux processing. With a lot of if you don't remove the low elevation satellites, you want to keep them in the processing. You can reduce the elevation angle cutoff, for example, from 7 to 0 degrees, and then all of the observations will be kept in your processing. So in this case, we will downweight the observations from satellites lower than 30-degree elevation angle. So then this downweighting is more significant for lower elevation satellites. For example, for 1 to 2 degrees, its downweighting will be tens of times larger than those satellites at 20 or 25 degrees. So this is the case. We do have real-time products to be saved in our online product repository. But the real-time product is not so stable because sometimes because of the network connection, we lost a lot of satellites, and then you have to tolerate. If you insist on using the real-time products, and then you have to tolerate the bad data processing precision because you have lost a lot of satellites due to the connection problem. So we do have the real-time products as well. That's RTS products on the same repository as that of the final and rapid products by the Wuhan University. So you can, but you cannot expect the similar data processing quality to that based on the rapid and the final product. But you can't make any real-time connection to the data streams. For example, the product data streams from IGS, from IGS RT. You cannot receive any real-time, for example, the RTCM streams for warbits and the clocks to be connected with our private PPR software, because this software is only for post-processing. But you can save the real-time warbits and clocks into SP3 file and a clock Redux file, and then use this real-time saved file to introduce them into our private PPR software to mimic still real-time processing. Next, number of epoch check tool. I think it's Jihan, how many epochs can the software tolerate? I mean, for example, the higher data. So how many epochs? 86,000.
It is depend on your observation time. It's usually the two when you use the loss editing mode, the minimum observation time required is about 2 minutes.
This is not his question. He means what's the longest duration of our software's capability in processing the Redux data? I mean, the 2 days or 3 days, 10 days?
It's 32 days now.
32 days for 30 seconds. So that means it's about I think 86, more than a few tens of thousands epochs, just approximate. Should the Redux file be decompressed first? Jihan, I think
yes.
we should. Yes, right?
Yes.
Yeah. You should decompress the Redux file at first before you can use the use the PPAR software to process. Because the decompressing is based on another open source software developed by a Japanese scientist. So we haven't included this module into our software. So you have to use some other software to decompress it. And the Rednex name convention important. Yeah, the Rednex name convention is indeed important because someone, if you use their own data, their own software, their own receiver to collect some data, they always use some non-standard naming convention. For example, just ABC, blah blah blah, and this kind of file cannot be recognized by the software because the software will use the file name to determine the time, to determine the epochs, and then use this time to determine what period of products to be downloaded. This just to facilitate the processing of the software, so we don't do any further accommodation of this kind of naming convention errors. And but you can use the short name and the long name both to facilitate the processing. It doesn't matter for long name or short name, but you have to follow the standard of the IGS for naming a Rednex file. That should be incorrect for non-IGS station. The multiple station for us is the anyway. We don't have any station information file in our software. We just use the header information from the Rednex data itself. I know what do you mean. The Gamut software and the Bernese software they both use the station information file. We used to have this one as well, but we finally abandoned it because we just want to make our software easier to be used by some junior users. You don't need to worry about any station file to overwrite the header information or anything. So I think for standard Rednex file, you should have the correct antenna information in the header part of the Rednex. But everyone has his reasons. But anyway, here we don't have this kind of function to override the Rednex headers. If your Rednex headers is vacant, then all of the antenna information will be set to 0. Super stands just how to do that. I don't have any way to go around WGET at the moment, but you have to use some other machines to download the WGET. Okay, I think we can still communicate through the Slack. I mean, we are all in the Slack community, and then you can also send an email to us using the pride at whu.edu.cn, and we are very happy to receive your email for complaints and as well as some kind of suggestions, so we can improve the software. But mostly the software will be improved based on the Linux version. We don't have any further plan to improve the Windows or Mac version because that will take a lot of time, and we have to think about all kinds of excursions in the development. So the Linux version will be maintained forever, and you can have some more recommendations in the software operation and its capability to improve your processing. All right. All right. All right, Melissa, I think we can close the session today, and we can meet each other on Friday. And thanks for your attention. And we appreciate your support of this software, and we really hope that this software can be used by all of you and in your work, and that can contribute a little bit to your future research. Okay, Melissa, I think it's yours.
All right.
Okay.